Good morning. So today we're going to go over one boundary value problem, a heat equation in cylindrical coordinates from top to finish to connect it with the Bessel functions and Bessel series that we talked about last time. I want to mention though the mistake that I discovered, the typo from the last part, kind of unfortunate because it's a small typo, but it's important to make this correction. I mentioned that already in the pin comment on the previous part, so the last part of the previous lecture. And anyway, the formula sheet that I asked you to actually print out, that's correct. So that's double check. So there shouldn't be any problem with it. So make sure you use the formula sheets on Bessel functions. But what happened in the previous video, I forgot to carry over a power of 2. So let me just mention it here. So the conclusion, when we talked about the orthogonality of Bessel functions, the conclusion was that you can represent a function via a series of Bessel functions. So let's put together a summary of the results on that part. And if you can check also with the formula sheet. So suppose you have the domain of the function 0 and c, which remember in cylindrical coordinates, that's typically the radius of the cylinder. And suppose we denote by alpha 1, alpha 2, alpha 3, and so on, alpha n, the roots of the equation J naught of alpha c equals 0. So again, remember, this is the source of our eigenvalues and eigenfunctions when you solve the Sturmovin problem. So, and again, this is for a Dirichlet type condition. We're going to have different types of conditions later, but this happens when you have a prescribed 0 temperature on the boundary. So with that in mind, so if alpha 1, alpha 2, alpha n, and so on are the roots of this equation, then if you have a function which is piecewise continuous, you can represent a function in terms of what we call a Fourier Bessel series in terms of these Bessel functions. So again, pay attention here closely. The alpha j's, alpha 1, alpha 2, alpha n, are the roots of this equation, right? When you have that constant c, which is the right-hand side of the interval. So once you have these roots of this equation, then you have basically the corresponding Bessel functions, which end up in the eigen functions for the Sturmovin problem when you replace then c with x, right? So the alpha j's are the roots of this. These will be the eigen functions. And so, as you will see later at the end of the problem, when you set up the initial condition, when you impose the initial condition after you do the superposition principle, you will need to figure out a way to represent a function in terms of these series. So because the Bessel functions, these ones are orthogonal, we concluded that yes, we can do this representation, and the formula for the coefficients aj, and this is where the mistake happened, is 2 over c squared j1 of alpha jc quantity squared. So I forgot this power 2. The integral from 0 to c x f of x j naught of alpha jx dx, where j again goes from 1, 2, 3, and so on. So these are the analogous to Fourier cosine sine series before, right? So this is the formula that gives you the Fourier Bessel coefficient. So this is a Fourier Bessel series. All right, so let's see how this comes together when we solve the heat equation. So let's do an example. And yeah, so let's say the u partial t on the left is equal to a squared, and then the Laplacian in cylindrical coordinates, 1 over rho u rho. You can call it cylindrical coordinates or polar coordinates, because remember, because of our simplification that the heat flows only across the radius, you can think of rho as being the polar radius, right? So for the object being a disk for all practical purposes, right? So the domain for rho is 0, 1 in this problem. So let's say the radius is 1. So again, pay attention here. That means in our formula, c will be 1. And of course, instead of x, you're going to have rho eventually, right? Because that's your variable. That's the notation for the cylindrical coordinates radius. So, and then let's say that the initial temperature is constant everywhere and it's equal to 5. To make it easy, our first example, notice, because this can be any function of rho, right? I mean, when it comes to impose this initial condition, we're going to have to find a Bessel series representation for just this constant 5. And then the boundary condition, which is just specify on the radius, is homogeneous. So let's say one of u of 1t is equal to 0 for t greater than 0. So this is a homogeneous boundary value problem. That's the only boundary condition you need. Besides the continuity assumptions, you just need to specify what happens at the boundary of the object, and then the initial temperature, which is 5 in this case. So how do we solve it? By separation of variables. And by the way, before we move on with that, let me just remind you briefly the two quick formulas that we might need later. The derivative of j naught of x is equal to minus j1 of x. And then the derivative of x j1 of x, so the derivative of the product x j1 is x j naught of x. Okay. So we might need this in the process later. So we already did the separation of variables for this. Let me remind you what you end up with when you do this process. So again, as with all separation of variables, you take the dependent variable and you assume it's in the product form of a function in rho and a function in t. Plug in the boundary condition into this. So if I plug in 1 for rho, I get r of 1, t of t equals 0. And since I want non-trivial solutions, that means r of 1 must be 0. The non-homogeneous condition, remember, is dealt with at the end. When I plug this into the PDE, remember, if I do the separation of variables, I end up with this equality of two differentials, t prime over a squared t, two differential equations, r double prime plus 1 over rho r prime over r. And remember, normally we write this as minus lambda, but in anticipation for how the eigenvalues will look like, let's call the separation constant minus alpha squared. It's going to be a positive number. I mean, yeah, there's, on the left is going to be a positive number when I move it to the left, so we might as well call it alpha squared. So the equation in t then becomes t prime equals minus a squared alpha squared big T. Keep this in mind. We're going to deal with that a little bit later. And the Sturm-Liouville problem will be the equation in R, which can be simplified if you rearrange the terms. Multiply by rho. And now you should recognize it as a modified Bessel equation of order 0. Modified because of this extra alpha squared. Without alpha squared, remember, its solutions will be j naught of rho. With the alpha squared, its solutions will be j naught of alpha rho. So from all the discussion prior to this moment, we knew that the solution is just a linear combination of Bessel function of the first kind, j naught of alpha rho, plus C2 Bessel function of the second kind, y naught of alpha rho. But automatically C2 must be 0, so later on you don't even have to bother by taking this into consideration. Just start with j naught of alpha rho. C2 must be 0 because, remember, R should be continuous. So we can't have y naught there because it's discontinuous at 0. So we left basically with the fact that the solution must be, and let's forget about C1 because we're going to bring that constant later when we do superposition principle. So the solution should be j naught of alpha rho. And C1 must be not equal to 0, obviously, because otherwise we will have non-trivial solutions. Otherwise we will have trivial solutions, right, if C1 is 0. So this is the solution of the Sturm-Liouville problem. Now it's the moment to impose the boundary condition and to find the eigenvalues and the eigenfunctions. What is the boundary condition? R of 1 equals 0, right? That's C, right? The radius. So R of 1 equals 0 means J naught of alpha times 1 equals 0, or J naught of alpha equals 0. So remember, in this case, C is equal to 1. And we know that this equation, in general, remember, if for any C, any positive C, as you can see here, this equation will have infinitely many positive roots. So let's denote by alpha 1, alpha 2, alpha j, and so on, the roots of j naught of alpha equals 0. So basically from now on, whenever you replace alpha with alpha j, j naught of alpha j will be 0. These are the eigenvalues. So moving on the next page, and make sure you pause if you want to see the, or rewind if you want to see the work done so far. So moving on the next page, let's write down here that the eigenvalues are alpha 1 squared, alpha 2 squared, alpha j squared, dot, 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 again, with j naught of alpha j equals 0. This is where they come from. And the eigenfunctions are j naught of alpha 1 rho, j naught of alpha 2 rho, dot, 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 j naught of alpha j rho, and so on. Okay, remember now the next step is to solve the T equation for every eigenvalue that you found before, alpha j squared. Now the T equation in this case is just an exponential, so go back to the T equation and plug in the eigenvalue, which is alpha j squared, so minus a squared alpha j squared t, and now you can introduce a constant of integration that you can call it, we can index it by j. Okay, so it's customary, by the way, as you notice here, that the index of these that goes to these eigenvalues to be denoted by j. That's how it's denoted in the formula sheets and in the book. So the solution big T of little t will be some constant, call it aj, e to the minus a alpha j quantity squared t, where again j is from 1 to 3 and so on. Make every effort you can to put this in the context of what you guys did with sine and cosine Fourier series, because it's really the same principle. If it feels really disconnected from that, you want to maybe revise some of the concept we went through before. But if you understood very well how the method of separation of variable works, as an overall process, this should basically look familiar. Now, the ingredients are different, of course, because they have different functions, but the principles are the same. So what comes after that? Well, what comes after that is the superposition principle. The only thing left to deal with is the non-homogeneous condition, that 5 temperature on the bound, the initial temperature equal to 5, right? So superposition means that now we're looking for a solution in the form of a series. So u of rho t is going to be a summation from 1 to infinity. Let's start with big T. So aj e to the minus a alpha j squared little t times the corresponding eigenfunction, which was j naught of alpha j rho. So this is how our solution will look like. The only thing left to do is to find aj. And aj will be again from the initial condition. So the initial condition states that u of rho 0 must be equal to 5. So if I plug in 0 for t, e to the 0 is 1. Therefore, this is the same as saying that I need a series representation in terms of this Bessel function for the constant function 5. So you think of 5 as a function in rho. So now you go back to the formula that I mentioned before. And you can look at your notes, but remember the formula states that aj should be equal to 2 over c squared j1 of alpha jc quantity squared, the integral from 0 to c. And I'm going to use now, well, let me actually write the formula because we're going to have to change x with rho because that's the notation in our problem. But this is the formula for a series representation for f of x, right, with those boundary conditions, assuming that alpha j comes from j naught of alpha c equals 0. So this is the formula. Let me put it here in a rectangle, because now I'm going to show you how we will apply it in your specific case. So your function is 5, so you're going to put 5 here instead of f of x. And remember again that the radius is 1, so c will be equal to 1. So in our case, aj will be 2 over 1 squared j1 of alpha j squared, right? Because there's no, c is equal to 1. And the integral is from 0 to 1. Rho, f of rho will be just the constant function 5. We can pull that out of the integral in this case. J naught of alpha jx, excuse me, alpha j rho d rho. Okay, so in some cases, this is as far as you can go if this integral is hard to compute. And by the way, in this chapter, notice that I'm going to only ask you to do this integral if you have some power of rho, because we have that recurrence formula for this integral. Otherwise, it's really difficult or maybe even impossible to actually solve these integrals explicitly. But if you have a power of rho, expect actually to go further and use that integration formula. So this is the time to remember that rho j naught of something can be written in terms of a derivative. But see, remember we had those rules in terms of x j naught of x or x j1 of x prime. One specific step that I would advise you to do at this point, because I think it will make it easier to apply those formulas, is to make a substitution so that j naught is evaluated at a new variable, so that we have j naught of x, not some constant times the variable itself. So do this step pretty much all the time when you are at this moment, namely replace, you can use x, y, whatever notation you want to make, but replace the inside of the Bessel function by a new variable. So make a little change of variable, like x is alpha j rho. Remember, alpha j is a known constant essentially, and rho is the variable. And that means dx is equal to alpha j d rho. So it's just a u substitution. This is going to be 2 over j1 alpha j squared. And let's change the integration bounds as well. So if rho is 0, alpha j times 0 is also 0. And what else? If rho is 1, the new bound is alpha j. Okay, moving on. What do we have inside the integral? Let me actually pull the 5 out so I don't carry it inside the integral. So 2 times 5. Rho from the substitution is x over alpha j, and j naught of x now, because alpha j rho is x, And pay attention here, d rho is 1 over alpha j dx. There's another 1 over alpha j dx. So let's continue. We have on the left 10 over j1 of alpha j quantity squared. We can pull also 1 over alpha j squared. Again, those are constants. And you're left with the integral from 0 to alpha j of xj naught. Now it's time to look at those formulas that I wrote on the previous page. And remember, xj naught is the derivative of xj1. So this integral can actually be computed completely because xj naught just happens to be the derivative of xj1 of x. And therefore I can basically integrate it right away. The integral of a derivative, it's this stuff between 0 and alpha j. So the answer for the coefficient will be xj1 of x evaluated between 0 and alpha j. And let's actually do it on the next page. Well, I'm gonna write it one more step here and then continue on the next page. So this is gonna be, if I plug in alpha j, that's gonna be 10 alpha j, j1 of alpha j on the top, and on the bottom alpha j squared, and then j1 of alpha j quantity squared. So if you look carefully, notice that alpha j cancels with 1 alpha j on the bottom, j1 with 1 j1 of alpha j at the bottom. So when everything is said and done, our AJ, our Fourier coefficient for this Bessel series, I'm trying to make this as neat as possible, which is not that neat, but within the limitations. So the final answer for AJ is equal to 10 over alpha j, j1 of alpha j. Okay, so obviously this is an easy example because you had a constant for that function. But then finally, the final answer then, when you put everything together, u over t is equal to the summation from 1 to infinity, 10 over alpha j, j1 of alpha j, e to the minus a alpha j squared t, j naught of alpha j rho. So for those of you who deal with Bessel function for the first time, to say that this is the solution of the problem kind of looks strange, because you end up with lots of variables basically, right? So, but this is the stuff that we have to live with. Remember, all these alphas are known roots, known numbers. They just cannot be represented in a finite form. I mean, they don't have a closed form, so to speak. You can only approximate them to any precision you want, but you don't really have to have an exact value. You just need to know that they exist. So as long as one knows that the Bessel function will have those roots, positive roots, you just can call them, in this case, with alpha 1, alpha 2, alpha 3, or any letter you want, and then be happy with the solution in that form. And of course, if you want, one has to actually approximate the solution, you have to use maybe computer algebra systems that will be able to approximate these roots. Or we can do it by hand and approximate the solution up to a couple of terms in the summation, and then maybe use some approximated values for the roots themselves. Most of the time with computer algebra system, you don't need to do that, obviously. One last remark. Notice that j1 of alpha j is not going to be 0 because, and that's an important remark, I think I mentioned it once, but it's worthwhile to write it down, because the roots of j naught of alpha, j1 of alpha, etc., do not overlap. Okay, so once the roots are actually come from setting j naught of alpha equals 0, then you don't have to worry about the fact that this appears in the denominator. So you don't have any division over 0. So this is in a nutshell the process of solving a boundary value problem with Bessel functions. Let me close this part, and we're going to have maybe a shorter second part. We'll see how it goes, in which I'm going to illustrate other types of boundary conditions. So I want to go briefly over the other two types of boundary conditions dealt with in this chapter and how the Bessel series looks like in that format. This is also in the formula sheet, so have it in front of you while I go over that part. So stay tuned.